Okay, so the topic is the indexing ambiguity in serial femtosecond crystallography, SFX, resolved using expectation maximization algorithm. This work was done by Haibong Liu and John Spence. So this is an overview of my talk. So first I will just, to help you to recall some SFX basics, and then we move on to the term of indexing ambiguity. And we understand why we have this problem from the symmetry, from the aspect of symmetries. And then we move on to EM algorithm, and we see how it works for the indexing ambiguity problem. And at last, we talk about the consistency and the robustness of this algorithm and conclusions. Okay, so before we go on to the term of indexing ambiguity, let us help you to recall some SFX basics. So SFX differs from the traditional X-ray crystallography in several aspects. So in traditional X-ray crystallography, we have the goniometer to rotate the crystal so that the oscillation series can be recorded. And okay, so in this way, we have full reflections recorded in the patterns, and the orientation of crystals are well controlled and well known. So basically, the whole complete data set comes from the same crystal. So we don't have that many stochastic variables as in SFX. However, in SFX, the nanocrystals are delivered in the single file liquid jet stream. So the diffraction patterns are recorded from all these crystals, but only diffraction stills. So to solve the crystal structure, we have to merge all the diffraction patterns from different crystals, and we have these many stochastic variables like crystal orientation, shape, size, and some other. So because the X-ray pulse is so short, for each diffraction pattern, only partial reflections are recorded. To solve the crystal structure, we have to merge all the diffraction patterns from different crystals. The SFX data analysis pipeline mainly includes heat finding, background removal, which are done by Cheetah, and followed by peak detection, auto-indexing, intensity integration, merging, and scaling post-refinement. These are all done by BioXFEL. And this work is closely related to auto-indexing part, which is quite crucial to the success of data analysis. Because without the correct auto-indexing, we don't know how to merge the data to form a full reflection structure factor list. So what is indexing ambiguity then? Basically, it refers to the fact that for some space group symmetries, we have multiple indexing possibilities if we just judge from the Bragg spot positions. And we can understand this from the crystal symmetry aspect. So the crystal structure is determined mainly by the lattice of the crystal and its basis. In other words, identical copies of bases located at all lattice points make a crystal. So let's look at the 2D example. So on the slide shows 2D rectangle lattice, which has a MM point group symmetry. So the symmetry elements include the rotation, the two-fold rotation axis, and the mirrors into orthogonal directions. And then we add the basis to the lattice. We can see that the basis also has the MM's point group symmetry. So the overall point group symmetry of this space group P to MM is just the MM. Because the diffraction pattern has the same symmetry as the real crystal structure, so that for the 4 reflections, indicated by the 4 black boxes, minus HK, HK, minus H minus K, H minus K, they are symmetric and they have the same intensities. However, if we consider different bases, we shift from the basis shown in the previous slide to this basis. So you can see that the point group of this lattice is lowered, because although the lattice has the MM point group symmetry, this basis doesn't. So the overall point group symmetry of this lattice is just 1. So in this case, in the diffraction pattern, although the positions of the 4 black spots do not change, the intensities are not equal. So, and also in SFX, only partial reflections are measured. And as we said, the auto indexer adjusts based on the peak positions, not the intensities. So without additional information, we have this indexing ambiguity problem. So we don't know, for example, in these 4 reflections, which is which. We don't know that, only judging from the positions of the black spots. So here is a very good visual example. Just looking at these 2 pictures, without further information, we don't know which one is the correct orientation, right? So what do we do? This way or this way? So basically, to solve the indexing ambiguity, we have to reconstruct or recover the correct indexing mode. So when does this indexing ambiguity occur? So it occurs when the lattice symmetry is higher than the space group symmetry. So this table lists several common space groups which lead to the indexing ambiguity. And here in this work, we focus on the PS1 data, which has the space group of P63. So for this space group, there are only 2 indexing possibilities, HKL, KH minus L. So one of them must be correct. We call it the consistent indexing mode, or the correct indexing mode. The other way, the twin indexing mode, is called alternative indexing mode. And these 2 abbreviations will be used in the next several slides. And this is a chicken-egg problem. Why is that? Because, as we said, judging only from the black spot positions, we cannot index the pattern. So we need further information, like the intensity. But the intensity is only obtained after merging all the diffraction patterns. And the merging is based on the correct indexing. So it's a chicken-egg problem. And the authors used the EM algorithm to solve this indexing and ambiguity problem. And why do we use EM? Because EM is very good at solving the chicken and egg problem, as we can see from the float chart. I just simplified this flow chart a little bit so we can better understand. So the EM algorithm first assumes a model, like a structure effect list, full reflection. And then it calculates the correlation between each pattern and this model. Because there are two indexing modes for each of the pattern, right? CIM and AIM, like we saw. So we have two correlations for each pattern. We choose the max one, the larger one. And then the larger correlation will give you the CIM indexing mode, and the smaller correlation corresponds to the AIM. And we merge the patterns in both for both CIM and AIM. In that way, we get the full reflection list again. So we update the model. If the update of the model is small enough, we are reaching the marginal efficiency. Then we terminate the program. If it is not, we keep doing this cycling, this loop. So this is an iterative program. So we can see from this flowchart that the EM algorithm assumes random initial model, and then it maximizes the likelihood function for each element of the dataset. The likelihood function here for this problem is just the correlation between each pattern and the model.
What do you call an element?
Like for here, one diffraction pattern is one element of the whole dataset. Yeah, this is just a general term. And it also provides the feedback to the next iteration because it updates the model in each iteration, and it continues this loop. So in this way, we don't care if we have a chicken or have an egg at first, because we just assume a random model, and we let the nature of this system to update the model. So how does this work? So to check if this EM algorithm works for the real experimental data, the authors calculated the past correlation between the reference model, theoretical model, which is calculated from the PDB data, and the merged intensities for both CIM indexing mode and AIM indexing mode. So the green curve is the correlation between the reference and the CIM, and the blue curve is the correlation between the theoretical model and this AIM merging intensities. The red one is just a target score, and it reflects the average of the highest correlation between each pattern and the model, theoretical model. So this provides a perfect error matrix for this method because we're using the experimental data from a known crystal. So we can use the PDB file for the known crystal to provide the reference. So you can see that after several iterations, like after 10 iterations, the artificial symmetry showing the pattern, you can see this is the mirror I draw, because as we mentioned, the indexing ambiguity is about HKL and KH minus L. So this pattern is cutting through the L equals 0 plane. So the symmetry is about this dotted line, right? And this is artificial before detwinning. After several iterations, you can see that artificial symmetry disappears. So that indicates the success of this EM algorithm implementation in this problem. Okay, because the EM algorithm is a randomized algorithm, right? Because it starts from a random model. So we need to test the robustness and the consistency of this algorithm. How to do that? The author just conducted 10 runs with a different random starting model. And you can see that after just several iterations, all these runs will converge to the same correlation for both CIM mode and AIM mode. So on the right-hand side, this is a table of correlation, internal correlation between the 10 runs, the Ambiguity data from Chufeng, and the twinned data. By twinned, I mean without this detwinning, without considering this indexing ambiguity. So we can see that inside these 10 runs, among these 10 runs, the inner consistency is quite high. Almost all of them are above 0.9, indicating very good consistency for the EM algorithm. And also, the correlation between this EM result and the result from the ambiguator is also good. Here, it's 1, indicating that the EM is consistent with this ambiguator in the crystal package. And the upper triangle shows the correlations between the AIM merging intensities. Because the AIM is actually the wrong indexing mode, so you can see that the internal correlation between these 10 runs are not very good. So you can see from the heat map. The authors also looked into let me see, the computation time and the number of patterns we need to provide the reliable results. So from the figure on the left-hand side, we can see that the computing time is approximately directly proportional to the number of to the size of the data set, number of patterns, which is quite good because it is not time expensive. On the right-hand side, it shows the percentage of the corrected indexing modes. So you can see that below, so if we have patterns less than 5,000, we have very large error, and the correlation between the reference data set and between the reference model and this merging intensity is quite big. So this means not quite reliable. But if we have number of patterns greater than 5,000, you can see the results are quite reliable and negligible error here. At last, the authors try to explain why this EM algorithm is improved upon this BD method mentioned in this paper. Because this method tried to reconstruct the correct indexing mode based on calculating the pairwise correlations. So the correlation is calculated between partial patterns. And the EM method calculates the correlations between each pattern, which has partial reflections, and the full reflection model. So you can see that the EM is much more powerful in distinguishing these two indexing modes. So it can recover the correct indexing mode, CIM, much better. And this probably explains why the EM method is improved upon this BD method mentioned in this paper, because it avoids the calculations between partial reflections, which is a big problem in SFX. So to sum up, although the partiality problem is very serious in SFX, it does not prevent the recovery of the correct indexing mode. And EM is more successful because the correlations are calculated between the pattern and the full reflection model. And the author also pointed out it is very important that the saturated peaks at low resolution must be excluded, because these the contribution from these saturated pixels can be very strong, and this can cover the sensitivity of the correlation to differences due to different indexing modes. So if you include these saturated peaks, you can sometimes be difficult to tell which indexing mode is correct.
Okay, no one else is discussing it. Okay, let's thank Chufeng again.
you can say